This video is an introduction to anti-differentiation. Some people call it determining the integral, and so we're going to look at what that is and look at some simple examples once we've established what it is. A couple of points that can frame this video. So for the first one, if we're given the rule for the derivative, can we find a rule for the original function to get us back from the derivative? Do we need any extra information, or can we just come up with an easy rule? Can we just reverse the derivative process? And an example might be if we're looking at velocity of an object, which is an application of the derivative. Can we reverse that as such, find the antiderivative and come up with a rule for its position? Because you might remember if we take the derivative of position or displacement, we can get velocity. And again, do we need extra information, or can we just go ahead? The process of undoing the derivative, reversing it, is called antidifferentiation, which seems fairly obvious, I suppose, doesn't it? Anti meaning opposite or the other way. Okay, so what I'd like for you to do now is pause the video and copy down the table. Now that you've copied down the table, in purple marks we've got some fairly straightforward questions because you know how to find the derivative already. We've got some power terms, so terms that involve powers of x. So if we have f of x, what would be f dash of x? Well, simply is 5. And the derivative of x squared is 2x. The derivative of 3x squared is 6x. 3x squared, 15x squared, and so on. So you remember how to do that. Basically, we look at any power term and to find the derivative, we reduce the power by 1, and we use the old power multiplied on the front to form the new coefficient in front of the x power term. How about going backwards? What I'd like you to do now is pause the video again, and it's important that you do this. I would like you to answer what should go in each of these spaces in yellow. Now you can see that the derivative f of x is already provided, but what would have been the original function? So you have several there to do. So pause the video, do them, and then compare them with my answers in a moment. Okay, so now that you've had a go at that, I guess we should get the same answers, shouldn't we? So the derivative of what gives 3? Well, of course it is 3x plus 110, isn't it? Wow, you might think, what? He's lost his mind. Well, I'm not wrong. 3x plus 110, the derivative of that is 3. I'm thinking some of you out there might have just put in just the 3x. They're both correct is the answer. In fact, thinking about it, doesn't matter what number constant goes after the 3x. So what about the next one here? The derivative of what gives 4x? Let's have a look. Is it 4x squared by raising the power by 1? No, it is not 4x squared, because if we take the derivative of 4x squared we get 8x. So it's actually 2x squared will give 4x. Okay? But we can have any number after it as well. I could say 9. You probably didn't have that answer. So what's going on here? The next one, we know it's got to be, well, we've got the power needs to be 1 higher, because when we take the square root of x squared we get x, but we've got a half on the front. So a quarter x squared works, because if we lower the power by 1 we get x to the power 1, and 2 times a quarter is a half. But again, you could have a minus 11 on the end and it'll still be the same, and so on and so on. So what gives? So what we're finding so far is that the number on the end, if there's a constant there or not, or if the constant is 0, you still get the same derivative. So we're sure about part of it, but unsure about the other part. So for this one here, we're sure about the 2x cubed bit, but we're unsure about, is there a constant, which could include 0. And so on. We could do that and finish off the rest of them, which I've done all by the last two, which is interesting. So you might remember when you take the derivative, you've got to actually you can take the derivative of each term separately in a sense. So we could try that for integration or for finding the antiderivative. So this first part would have to be something x squared, and by putting a coefficient on 3 on the front, that would make the 6x. But again, we could have any constant there, and with the 11 it'll be 11x. But again, there's constants there. So it looks like we might be able to treat finding the antiderivative in the same way by separating the terms. So you might have found that a little bit, uncertain in nature. What we're getting is an answer with some sort of constant on the end. So we get some sort of answer, which we're sure about, plus a constant. And you can just name whatever constant you like. One way of looking at why this happens is to look at a graph. So one of the questions we looked at before had an x squared term in it. So you might remember too that the derivative, dy dx, is also known as the gradient function. And that can help us explain to some degree what's going on. So if we have this family of functions here, y equals x squared, then y equals x squared plus 1, y equals x squared take 1, there's another one, y equals x squared take 7. They're all families, they're all from the same family, y equals x squared plus or minus some constant on the end. They have the same shape, you might remember, but they've just been translated up and down a certain number of units. If you took the derivative of each of those functions in green there, you would get 2x. All of them would give you the same answer, 2x, and that's because at a given point they all have the same gradient. So you could put tangents there, and the gradients of all the tangents are the same at that given value of x, and that's true for any given values of x because they all have the same gradient function. So if we wanted to find the antiderivative of that, we could have an infinite number of answers. All of these here are answers for the antiderivative. But of course, you could put any real number on the end. So there's actually an infinite number of solutions. So that presents us with a challenge. So to start formalizing this, we need to look at Leibniz and what he started to do. He used that symbol there to mean integral. In fact, the symbol's got two parts. The symbol is broken into 2 bits and it has a function sitting in the middle. Okay, so the 2 purple parts there are the actual symbol. So it had, that's the symbol for, or the Leibniz symbol for the antiderivative, or sometimes called the integral. So it says the integral of 2x with respect to x. That's what the dx means with respect to x. So with respect to x. You need to tell the reader which variable you're integrating with respect to use the notation correctly. But we just saw that when we did that with 2x, we'd get x squared plus some constant. We saw that just back here, didn't we? Okay, there's all the green ones there. So, and that's by no means all of them. So we can write the general antiderivative of 2x with respect to x is equal to x squared plus c. So that's what that means. Or in other words, the indefinite integral of 2x with respect to x is x squared plus c. So indefinite integral and general antiderivative. Now it's called indefinite or general because of the plus c. That means it has an infinite number of answers. So we write the plus c as part of our answer. In set notation, we would be writing the integral of 2x with regards to x, or integral of 2x dx, is the... Okay, so we've got the primitive, which is f dash of x, capital F, also known as the indefinite integral or just the integral, and the general antiderivative. And remember, the symbol has two parts on it. It has the squiggly S looking shape and the dx, and the S shape actually is a stretched out S like that, and later on we're going to see that that means summation when we start to look at a graphical and geometrical explanation for this. So it alludes to summation. That's why it looks like an S. So another way of looking at it, if you have f of x, y equals f of x, the antiderivative of dy dx is y. So it undoes the derivative, is another way of explaining it. Okay, so it's reversing that derivative to get y or just f of x. And remember, plus c. Now we're going to look at just some basic power terms. The rule we follow is here. Now when we were going through our investigation with the table at the beginning of the video, this is actually what we were doing to find it. We might not have realized, but we had to go back to the original function before the derivative was applied. Instead of taking off one, we have to add 1 to the power, and we had to divide by that new power. So that's an important rule to note. Okay, now n can't be -1 because you'll end up dividing by 0. That gives a different sort of result, which we'll look at in the future. One of the questions from the quiz was this one here. Let's see if we can do that with our new rule. So we have to find f of x. If the derivative is x cubed, what would be f of x? So in other words, we have to find the antiderivative. So the general antiderivative of x cubed with regards to x equals, so we need to, what's a? A is the constant or the coefficient on the front. Well, it's understood to be 1 there, so we don't need to write that down really. So we need to add 1 to the power, so that'll be 4 over that new power, 4 plus c. So it's x to the power 4 over 4 plus c is the antiderivative. Last one. So one of the other ones was that one, so we have to find the integral of 3 over 2 times x squared dx. So the antiderivative, or the general integral, we've got a there, and we've got a is 3 on 2. We have the power, which is 2, so we've got to add 1 to the power and divide by the new power, and we've got 3 over 2 there. So that means that we've got 3 over 2 times x cubed over 3 . That will be 3x cubed over 6, or in other words, x cubed over 2.